At first glance, this looks like a simple pulley, right? But what if I told you the physics hidden inside this little diagram is the exact same principle that lets a single person hold back a massive ship? This is a classic mechanics problem, but it has a twist that trips up a lot of people. Today, we're going to crack the code and solve it together step by step.
All right, so here it is, problem 1.93 from a pretty tough physics collection. You see two masses, a thread, a pulley, looks standard. But then you read this one little sentence. There is friction between the thread and the pulley. And boom, that changes everything. That single detail is the key to the entire puzzle. So if problems like this have ever made you scratch your head, don't worry, we're going to make this crystal clear.
So here's our game plan for today. We'll start by uncovering the secret of this pulley. Then we'll solve part A, finding the friction coefficient. After that, we'll unpack the math a little bit, tackle part B to find the acceleration, and finally, we'll zoom out to see the huge principle that's really at play here.
So what's this big secret I'm talking about? Well, it's all about friction. See, in your intro physics classes, you almost always deal with ideal pulleys. You know, the ones that are massless and frictionless. But this problem is different. Here, the friction between the thread and the pulley is the star of the show. It's the whole reason this problem is so interesting. Okay, this slide right here highlights the #1 trap that students fall into with this problem. For a perfect frictionless pulley, you're right to assume the tension is the same on both sides. T1 equals T2. But with a real pulley that has friction, the thread actually has to grip the surface. This creates a difference. The tension on the pulling side, T2, has to be greater than the tension on the resisting side, T1. This is the absolute most important thing to get. T1 is not equal to T2. Let's dive into part A of the problem. Our mission is to find the friction coefficient, which the problem labels K. And it gives us a super specific scenario to look at, the exact moment the thread starts to slip. This slipping point is really a state of delicate balance. Just imagine the heavier mass, M2, is just heavy enough to get the thread moving. If it were any lighter, it would stay put. Any heavier, and it would start accelerating. We're analyzing that perfect, razor's edge moment where the pull from gravity is perfectly balanced by the maximum possible force of static friction. And here's the crucial clue the problem gives us. It tells us that right at that tipping point, the ratio of the heavy mass to the light mass is equal to this specific value, eta naught or eta naught. This single number is hiding all the information we need about the friction between that thread and the pulley. Okay, so how in the world do we get from a simple mass ratio to a friction coefficient? The tricky part is that the friction isn't just acting at one point. It's spread out all along the curve of the pulley. This is where we need a tiny bit of calculus, but trust me, the logic behind it is really straightforward. So this is the puzzle we have to solve. We can't just use our basic friction formula because the tension is always changing and the direction of the normal force is always changing as the thread wraps around. So what's the strategy? We use a classic physics move. If a big problem is too hard, you chop it up into tiny, manageable pieces. So first, we're going to zoom in on one tiny little segment of the thread on the pulley. Second, we'll look at the forces acting only on that piece. You've got tension T on one side, and on the other, friction has added a tiny bit, so it's T plus dt. Third, we write out the force balance for just that tiny piece. And finally, we just add up the effect of all those little pieces, which is what integration is.
And all of that analysis boils down to this beautifully simple little equation. This is our secret code. It basically says that the fractional change in tension, that's dt divided by t, at any point on the curve is just proportional to the friction coefficient k and the tiny little angle d alpha that piece of thread covers.
So when we integrate or sum up that little equation over the entire area where the thread touches the pulley, which is half a circle, or pi radians, we get this fantastic result. The friction coefficient k is just the natural log of that critical mass ratio, eta naught, divided by pi. And just like that, part A is solved. Pretty neat, huh?
All right, part A is in the bag. Time for part B. Now the situation changes a bit. The mass ratio, M2 over M1, which we'll now just call E nu, is bigger than that critical value E naught. So what does that mean? It means static friction can't hold on anymore, and the whole system is going to start to move. It's going to accelerate.
Now, you might think that since everything is moving, all our old rules go out the window.
But here's the really cool part. The physics of the friction doesn't actually change. The relationship we found between the two tensions, that's set by the friction coefficient and how much the thread wraps around the pulley. So even though the system is accelerating, the ratio of the tension on the tight side to the tension on the slack side is still governed by that same factor, which we already know is E to naught. That's the key to cracking part B.
So now that we have our tension relationship locked in, we can go back to an old friend. Good old Newton's second law, F equals ma. We're just going to apply it to each of the two masses one by one, and that'll let us find the acceleration of the whole system.
Let's just picture the forces, right? For the heavy mass, M2, gravity is pulling it down with M2g, and tension T2 is pulling it up. So the net force is M2g minus T2, and that equals M2a. For the lighter mass, M1, tension T1 is pulling it up, and gravity is pulling it down. So the net force there is T1 minus M1g, and that equals M1a. So check this out. We have the two equations we just wrote down from Newton's law. And we have our third equation from the pulley friction, T2 divided by T1 equals E to 0. That gives us three equations, and we have three things we don't know, T1, T2, and the acceleration A. That's it. The physics is officially done. The rest is just plugging and chugging through the algebra. And when all the algebraic dust settles, you get this really elegant final answer for the acceleration. Look at it. It's just gravity, g, times this fraction that depends on the difference between our actual mass ratio, E, and that critical slipping ratio, E naught. And check this out. If E equals E naught, the top part is 0 and the acceleration is 0. That makes perfect sense. So we solved the problem, we got the answer, we're done, right? Well, let's not pack it in just yet. It's worth taking a second to appreciate the bigger idea we've just worked with. Because this isn't just some one-off trick for a textbook problem. It's a really fundamental principle in mechanics. So what are the big takeaways here? First, friction over a curved surface doesn't just subtract force. It actually creates a tension ratio. It acts like a multiplier. Second, that core relationship holds up whether things are standing still or accelerating. And third, we saw just how powerful calculus can be. To understand a complex system, you analyze one tiny piece and then just sum up all the pieces. You know, this powerful idea actually has a name. It's called the Capstan equation. It says the tension on the high side is equal to the tension on the low side times E raised to the power of the friction coefficient times the wrap angle. In our problem, the angle was pi, and that whole e to the k pi term was just our eta. This equation is used all over the place in engineering and physics. And this is why this stuff really matters. The Capstan equation is the reason a sailor can just wrap a rope around a post a few times and hold back the incredible force of a giant ship. Each extra wrap multiplies their holding force exponentially. It's the same physics that lets a rock climber, using a little belay device, easily hold the entire weight of a falling partner. The friction does almost all the work for them. So there you have it. You've cracked the code on pulley friction. But what's the next level? What would happen if the pulley wasn't weightless? What if you had to use some of that force just to get the pulley itself spinning? That's a great thing to think about for next time. Thanks for working through this with me.